Okay, yes, so good afternoon. So a slightly different sort of talk here. So this is generated out of my personal interest. My sort of role at the university is mainly a teaching one, but of course what I can do is use this in offering final year projects and sort of feed that back into the educational loop. So string bed measurement, and really what I'm after is actually a method for measuring the full response of the string bed. So to date, lots of information is available on mode shapes. The frame has been analysed extensively. So what I was doing when I first set about this research, and what I present today is only a snapshot, it's not the end game by any means, is really to look at what research has already been done. Lots have been done on mode shapes, so there wasn't really any need to sort of go back into that. And you can find mode shapes whether you have something in free suspension or whether you actually have something which is clamped. But the details on that are well established. So I thought it would be nice to actually look at a different area, particularly the string bed, because ultimately it's the only part of the racket that's in contact with the ball. But why? Why then look at strings? Slightly obscured, but we can see just along the top, we actually have a whole range of materials. So this is a natural gut or cat gut. Then we go to hybrid strings, and these are strings which try and simulate what's actually happening in natural gut. Then we have polyesters going through to more synthetic gut, Kevlar. So there's a whole range of materials, and the question I ask myself is why? Why do we have so many materials? In addition, why do we have so many different forms of construction? And if you're a player trying to choose a particular string, how do you actually decide which one to use? So the manufacturers, what they do to guide you on this is they give you a scale, something like this, and this is just zoomed up, and what it says along the bottom here is a range of characteristics for the string. It's power, comfort, control, durability, and performance. But what actually does that mean? And this really is the basis of what I was looking at, because of course it means nothing, because there are no system international units, so how do you possibly compare one string to another? And in addition to that, you then also have the different thicknesses, or as we like to say in tennis, you have different gauges. So 15 is the largest diameter, it actually goes down to 18, but very few players actually use that. So we have these things to consider. And then in addition to that, you also have different types of racket. So here we have one which is a Prince, used by Chang. Only has 14 main strings, so the main strings are the ones that run parallel to the handle, the longest sort of axis, if you like, on the ellipse. But then we can have other string main quantities going up to 20, but 16 is generally the preferred one. So again, how does this actually affect the string bed? So this is what I was trying to tackle. I wasn't the first one to sort of start questioning this. Some work that had been done nearly 20 years ago decided to look at the different materials by just analysing a single string. So one at a time, they would actually impact the string, and they would actually produce a range of responses. And natural gut is quite good because, as this particular test shows, that actually retains tension the best of all the strings. It's very expensive, so a natural gut restring, just the material might cost 40 to 45 GB pounds, but the average synthetic gut might only cost £10. So you're getting a much increased price for the natural gut, but the reason why perhaps a lot of professionals are prepared to pay this extra amount of money is because it retains tension. So the sort of feel that you would have as you go through a match would remain constant. But again, this is very subjective, there are lots of variables, but this is what was found out for single strings. And in the work, the conclusion, one of the conclusions, was this statement here, that although the work has started to discern between different materials, it actually recommended that you should look at the behaviour of a fully strung racket. So with that, I then move forward to then consider the string bed, but other research that has also looked at the string bed by bouncing a boule onto the string bed, measuring the coefficient of restitution, actually kind of dismisses this, and it dismisses it largely because it says that the string bed is almost totally elastic. So because it's totally elastic, they then have models like this where the string bed is only considered to be a spring, and there is no damping part in there. But I thought, well, if you have so many different types of materials, is this actually something we can look at? But of course it's quite tricky because how do you actually determine this? Another thing that you would have observed is Roger Federer, probably the one who did this most consistently, probably 5, 6, maybe 7 years ago. At the change of balls, he always changes his racket. So the first 2 games are counted as the warm-up. So your first 7 games plus the warm-up, he does a racket change. And then it's every 9 games when they change the balls, he always changes his string. So I thought, well, why does he do that? Is it purely an idiosyncrasy, or is there something else that is going on that he knows that we don't? But nowadays, more players are starting to do this. But again, it goes back to what's actually happening in the string bed. So, how do we do it? So, are you going to have a contact method, which is something that was done here by Haig, again, almost 20 years ago, where they actually attached some markers to the string bed, and then they impacted the string bed. And the output essentially of this work was purely to create a model which looked at the maximum deflection. And even with these aluminium markers and a high-speed camera, they were able to deduce that the deflection was very similar, very close to the model. But of course, once you have all these attachments, it's then difficult to look at anything beyond that, because obviously you're starting to disaffect the response. So with this in mind, what we did in the early days is to say, well, if we're going to attach something, and this was pretty good for maximum deflection, can we use this principle in the form of a linear variable displacement transducer, where the actual basic setup is there is no contact between the armature of the LVDT and the primary and secondary coils. So we thought, well, let's give that a go and see how that actually works out. So the basic setup would be the LVDTs would be attached behind the racket. You have here a high-speed camera, because one of the issues with the LVDT is that you have to have a carrier frequency. And the carrier frequency against the physical or mechanical measurement is only given as a rough approximation of 10-to-1 accuracy. So we weren't sure whether this would actually be able to respond quickly enough to the vibrations of the tennis racket. We then took a bowler machine, which is actually used for launching cricket balls, chopped the legs down basically so we had a sensible height, and then fired tennis balls at the string bed. We had to have a little bit of distance, and the reason for that is quite simple. It's because the ball, once it comes off the racket, if this machine is too close, it then starts ricocheting all around, so we don't want it then to affect our own results. But again, this is the basic setup, and the trick really as well, although this machine is quite consistent, the problem is how do you constantly hit the centre point? But at a certain speed, around about 30 miles an hour, we were able to do that. So here the initial results show that this is the armature of the LVDT, but with this type of attachment, the impact force was sufficient that it actually broke away from the string bed, so it had the initial displacements, but then actually couldn't track the rest of the response. So this was okay, but it actually obviously wasn't going to give us anything meaningful. So what we then did is to say, well, let's just try and track it completely and see what we get. So we had a steel bolt. We actually cut this, there's a splice that goes along the length of the bolt, so we can put that over the string and then clamp it up. So we have this sort of attachment. And now we can see that we actually get a full response of the string bed. We compared that to, sorry, this is the LVDT, we compared that to a high-speed camera, just to be sure that it's actually giving us a true response and that it's not disaffected by the carrier frequency ratio. But clearly that wasn't enough, because we still have a mass here which we want to reduce. But just to give you an idea that, of what sort of response we had, we can see at least that the armature is tracking the string bed completely. So we can say, well, that's not a bad first step. But then what we did is to change the attachment, and by reducing the mass, we're then getting something that will start to closely follow the string bed, and therefore it's giving us something which is a little bit more meaningful. And the idea was, if this really worked, we could have a series of LVDTs and look to see how the response is varying along its length. But with the change in mass, we were able to sort of predict, by just plotting a polynomial through there, we can see that this frequency actually would be about 400 Hertz if we actually had no mass whatsoever. So this was something we were aiming at, but it's obviously quite tricky to get something down to that sort of level of mass, reducing right down. So here's the LVDT. We look at the shape, and what that actually tells us is that there's excessive Coulomb friction. So there's excessive Coulomb damping with this triangular pattern, and I think what was actually happening is the string bed doesn't just oscillate backwards and forwards, it actually oscillates slightly off centre. And what was happening with the armature, it was catching on the coils, the primary and secondary coils, and I think that the deduction was that that was disaffected results from the excessive Coulomb friction. So, simple discrete model gives us a similar sort of frequency to what we were getting from the LVDT. So that just proves that really it's the mass is dominating, whereas if you actually looked at a partial differential equation, you're getting higher frequencies, and we should be expecting something 550 to 600 Hertz. So with that, we thought we need to really abandon this particular method. The other thing which was quite useful though is dwell time. Dwell time is useful because it's the time that the ball actually spends in contact with the strings. And you might think it's quite long, but it's actually only a few milliseconds. So everything that happens in terms of the direction and spin of the ball happens in around about 5 milliseconds. Now here's an early experiment by Brody. He has a specific experiment, and this is often what happens in tennis. People set up experiments just for a specific quantity. So they use lasers to predict how long the ball was actually spending on the string bed. So although the LVDT didn't really work very well, if we look at the response, the early part, it's very similar in terms of milliseconds of dwell time to what was actually being set up here. So we're only looking, we say that the ball leaves the strings at this point, and there's compliance of the ball, so we're getting sort of parabolic initial state at the beginning. We're still looking around about 6-7 milliseconds. So the contact method, i.e. contacting with the strings, probably had its day, and then what we did is we moved on to a non-contact method. So we used the same camera, slightly different rig, because the difficulty, the uncertainty was, will it actually capture the displacement of the string bed completely? And what we found is we were able to adjust the settings wildly to finally end up with a setting which could give us a complete response. And then what we did is put that through some FFT, some Fourier analysis software, and it's then giving us a single frequency of almost 600 Hertz. So this is actually more in line with what we'd actually expect. And then we decided to proceed along with this method by then looking at, here we have a response of frequency against tension. There's natural guts. We have, here we have polyester, and this one which is obscured is synthetic gut. And we have sort of marginal differences, and all of these results are taking immediately after stringing, plotting the frequency, because what we then can do is we know that the frequency is proportional to tension, and we can then start to compare whether this method has given us something that adjusts to these fine variations. Because as I said at the beginning, the key with this is about trying to discern whether there are, or whether we're able to generate a method which picks up on these subtle differences. So this is promising, and with that, what we can then do is look at the characteristic. When you actually string a racket, what players will actually do is use the initial tension at which the racket is strung as an indication for how it will actually play. And this often causes to an uncertainty, because what happens during the stringing process is you lose about 30% of the tension. So we know this. So what you're actually playing with is a lot less than what the stringer has actually strung at. So here's a formula which looks at frequency from the membrane model. This is the strung tension, and this is actually what we're getting. So this is the frequency of what we're actually measuring. This line, which you may not be able to see, equates to 30% of the initial tension, but of course what we're getting for this particular type of synthetic gut is indeed much lower than that. So if nothing else, we can begin to look at what you're actually playing with as a tension during play by using this type of result. The effective string gauge, so inversely proportional to frequency will be the mass. So here we have a test on the synthetic gut. This is a 17 gauge, so it's a thinner string, and as we would expect, the frequency should be higher, as opposed to the 16 gauge material. So again, it's able to pick up these subtle differences and giving us a lot more confidence that the method that we're using is actually working. Dwell time, again using the high-speed camera, the non-contact method, we can see that the dwell time is actually reducing in milliseconds from around about 7 down to about 6 milliseconds as you increase the tension. Again, these are very small differences, but the results are sort of strongly suggesting that it's able to detect how the dwell time changes, and this is what we actually had with the LVDT. So it compares reasonably well. So as a method, again, it's giving us a little bit more confidence that actually this is the way to go. Another quantity which is quite important with strings, because these are viscoelastic, is dynamic stiffness. But how do you measure it? The stiffness on normal engineering materials is very easy to measure because you can use an Instron machine, you can apply a load, measure the deflection, and the stiffness is then calculated very easily. But for a tennis racket, how do you actually apply the force that quickly? It's happening much, much quicker than any piece of apparatus that we have available. So I just explored the idea of using the dwell time, the force generated by the ball, and just to predict what sort of dynamic stiffness you're actually getting. So this was for a range of tensions, so 37, 50 and 65 pounds. And they're actually appearing roughly in the right sort of order, the right sort of dynamic stiffness that you would expect. So the higher 65 pounds are coming up at the top sort of stratum, and then you're going down to 37 pounds. So at least the results are in the right sort of shape. So again, it might be something we can explore, but the problem is during that process, some of the energy is actually being lost to the ball. So although this is quite nice, I acknowledge it's a very difficult thing, it isn't the answer, but it might be something we can improve upon with future testing. So the high-speed camera, the non-contact method would actually have an impact that looks something like that, and we can see the vibrations are absolutely tiny after impact, but at least the process is able to pick up on these, and it might be something we can do more analysis with. And then that takes me on really to the conclusions. So from the methods that we had, the LVDT, it sort of proved an initial sort of exploratory purpose, but very little more. The high-speed camera certainly seems to be the way to go. But some of the findings that we have show a little bit of promise, but clearly we're not quite there yet. So Rafa Nadal will have to wait a little bit longer. Thank you very much.